Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovitz. In The Expanse, humans have colonized the entire solar system, and yet, with all that space, we're still at each other's throats. But Cornell engineer turned showrunner Niron Shankar does an excellent job of keeping all that space travel grounded in real physics. Today, we're talking to Karen Masters, Allen Liu, and Charles Liu, authors of 30-Second Space Travel, a book I really enjoyed, but unfortunately, so did my dog. Let's jump right in. In Star Trek and most of the other space operas, humanoids zip across the galaxy faster than the speed of light because their ships have some form of inertial dampener that keeps everyone inside the Enterprise or the Millennium Falcon molecularly intact. So Karen, in real physics, why can't we move faster than the speed of light without dying?
Well, it's not really about dying. It's actually about getting to the speed of light at all. And so what we believe is that there's this real speed limit in the universe. You just can't get to the speed of light if you have mass. Weird things start to happen. Your mass starts to increase, basically. And so this is part of Einstein's theory of relativity, that as you get closer to the speed of light, your mass starts to get much, much bigger. And so the energy needed to accelerate you gets ridiculous. And it just becomes impossible to get to the speed of light.
Because we get so much bigger that we can't generate the force to move forward. That's right,
yeah. You can't, you basically would need infinite energy to accelerate a spacecraft to the speed of light. And so, in Star Trek and Star Wars, they invent these like hyperdrives that kind of sort of skirt around that. What's nice about The Expanse is they don't actually do that.
In Shankar and James S.A. Corey's vision of the future, spaceships don't move faster than the speed of light, but they do use an Epstein drive, a modified fusion drive invented by Solomon Epstein, a fictional scientist. Dr. Epstein, who again does not exist, pontificated that using a magnetic coil exhaust acceleration, a spaceship can sustain thrust throughout the entire voyage. And none of that is real. But Alan, why is continued acceleration a good thing?
Well, the longer you can accelerate, the more speed you can gain. So you can start slow and start from whatever orbit around the planet you're going to, and then you can thrust throughout the entirety of the void. You can get to your destination much, much faster than if you only thrust very at the beginning and the end, like our current spaceships do.
So if I'm moving through space and I have my cruise control set for 50 miles an hour, at that continued exertion, am I going to start moving faster than 50 miles an hour?
Yeah, so the thing about space is because there's no friction to slow you down, there's no air, there's no road to provide that friction, then what happens is that you actually, if you keep your accelerator at the same level, you just keep going faster and faster and faster until you get to your destination or until you start to slow down because you don't want to crash into something.
Or my mass gets too big.
Or your mass gets too big and you run out of energy.
Right. Yeah. So, and what about the thing that they have when they don't put on the brakes? They have something called a flip and burn. Why is that?
Yeah, again, there's nothing to brake against in space. So on Earth, we brake against the road, so the friction of your tires on the road. And then also some spacecraft will brake against the atmosphere of the planet that they're trying to reach. So that's why we have these big heat shields on most of the spaceships that you'll see, like, the ones SpaceX is sending up and so forth. But if you're just coasting in the vacuum of space to somewhere like an asteroid with no atmosphere, the only way you're going to slow down is by expending the same fuel that you would use to speed up. So you have to essentially halfway through stop accelerating and start decelerating, otherwise you're going to crash.
At halfway through?
Yeah.
So this is a really serious slowdown or a very slow slowdown?
Yeah, the idea is that if you spend half your time speeding up, you get to a certain speed. It'll take the same amount of time that you spent speeding up to get yourself to slow down. It might be a little bit less because you've spent some fuel and your spaceship is lighter now. But essentially halfway through, you have to start slowing down if you want to reach your destination with zero speed.
Would the Epstein drive be hard to actually achieve in real science?
Yes. Yeah. Yeah, the amount of energy that you need is like colossal. I was looking on some calculations people have made. It's like you need the electricity grid of a whole continent to power one spaceship.
It's kind of the thrill of some of these space operas, though, is that their consumption of energy is so bourgeois.
Yeah.
I mean, they just
lackadaisical, shall we say?
Yeah.
No, it's really true. The key, as you know, right, is consistency. If they are self-consistent within their own universe on how much energy or how much speed or how much fuel they expend, then we can suspend disbelief reasonably well. When you have a circumstance where you have a little tiny ship that can go across the galaxy in 15 seconds and the big ship that goes across that same distance in the same amount of time, then you start wondering, wait, what happened to the motion and the Newton's laws of physics and things like that actually govern the motion?
Right. If a piece of art sets the rules and then follows the rules, we're all good. Hobbits all have hairy feet.
Yeah.
Right? And there's always this sort of scope for, you found something that suddenly has this amazing energy density. And, we have had revolutions in energy, right? Even, the difference between solar panels today and 50 years ago is astonishing. And so, maybe several hundred years in the future, there will be an energy source that can power this kind of drive.
In most space operas, the engine is in the rear, and it's very beautiful to watch as they push the ship forward through the vacuum of space. But in The Expanse, the ship's engines sit perpendicular to the ship's floor. Why does that location matter?
Yeah, so you sort of get pushed back into your seat by acceleration, right? So if the engine is behind you and it's thrusting continuously for weeks on end, then instead of feeling like you're being pulled down into the floor like you'd want to be, like your legs are built for, you would essentially be stuck in your chairs for weeks and you wouldn't be able to do anything, and it would be really frustrating to get around the ship.
Kind of use it like effective gravity.
So it's for gravity, not acceleration.
Well, there's a sort of the same thing.
Why is gravity and acceleration the same thing?
There's a thing called the equivalence principle.
Yeah.
Albert Einstein made it one of its tenets in his general theory of relativity. Basically means that on scales that we live in on a daily basis, say on a planet or on a spaceship, you actually cannot tell the difference between gravity, which is the curvature of space-time due to mass, and acceleration, which is a push or a pull. So that's why if you're moving this way and you're being accelerated in one way, you can actually feel just as if you were pinned to that surface, as if you were pinned to a planet's surface by the gravity exerted by that planet.
Sure, and we all experience that when somebody hits the gas really.
Yeah. Boom! Yeah.
Right.
Or in an elevator, right? You feel a bit heavier when it goes up and a bit lighter as it starts to go down.
The Expanse is based on a series of sci-fi novels by James S.A. Corey, the pen name of co-authors Daniel Abram and Ty Frank. In an interview, Frank was discussing other shows that use artificial gravity only to make their spaceships more livable, and he said, the ability to create gravity fields out of nothing is literally a humanity-changing technology that should have effects on everything you do. And I do not understand why. But lucky for us, our guest, Karen Masters, is writing a book on gravity. So, Karen, why is gravity a humanity-changing creation?
Well, that's an interesting question. I think in terms of space travel, we know that humans evolved on a planet with gravity, and so if we are out in space without gravity for long periods of time, we know from astronaut studies that can have detrimental health effects. So astronauts have experiences where the fluids in their body kind of redistribute and end up in their head. They get stuffy heads. They might feel nauseous. When they're up there for a long time, they experience bone loss and muscle loss. And so, it's not good for humans to be outside of gravitational fields for a long period of time. So if you're going to live in space, you need, the ability to generate gravity is kind of important. In terms of being on Earth, you can imagine, the ability to turn off gravity and sort of be able to float around and move materials with very little energy would be really life-changing, right? So, just being able to control gravity in some way, I think, would be life-changing. And we have, there's nothing that we know about that could actually do that. So,
if we could truly control gravity, could we create a planet?
Interesting. I mean, that
It'd
is
be a terrible idea.
Yeah.
It'd be a terrible idea. It'd totally mess up everything else. A new planet, but.
I mean, that is how planets form. They form from gravity pulling the material together. So I guess, why not?
In The Expanse, the large ships use centrifugal force to create the artificial gravity in the ships, and I think I've been on that ride many a time at a carnival.
Yeah.
But in space, would that really work, and is it the same thing?
Yeah, it's the same principle as the carnival ride. The idea is that if you're constantly turning, your inertia is pushing you into the floor of whatever's you're turning around. And that gives the same sensation as being on a planet with gravity.
So it's the turn, because
Yeah.
it feels like when you're on the ride that it's something coming at you.
Yeah. So it's because you're turning along with it, you're sort of the rotational aspects of those sort of cancel each other out. So while you're sitting there on the spinning object, on the carnival ride or on the spaceship, the force that you feel exists is pushing you right backwards away from the center.
I demonstrate this to students with a mass on a string. And, so you can prove that I can spin it around my head quite safely while I hold on to the string. But if I let go, it's going to shoot off in a straight line. We all know that intuitively. And that is a demonstration that there's a force pulling it around in a circle. And so that force, that acceleration is creating the same effect, this equivalence principle, the feeling of gravity.
So points for Mr. Shankar for nailing that.
Yeah.
Niron is very good about a lot of these things.
Yeah. Yes, he is very good, and he's very detailed. And sometimes the gravity that they simulate is weird. Like in this clip from season 1, episode 2, Detective Miller has to do some pretty fancy pouring to get the booze into his glass. So, Karen, what would make water or any liquid arc like that?
I mean, this is a really nice little demonstration, and I think it's exaggerated, but it's still, an exaggerated version of something we call the Coriolis Force. And we do have this here on Earth. So the Earth is a sphere, right? And so if you think about it, if you're on the equator, you have a slightly longer distance to go around once than if you're on the pole. You don't go around as far, right? And so that difference in speed that you need to be part of the rotation at the equator and away from the equator creates this kind of turn. And we see it in hurricane scale things on Earth. So hurricanes in the north always turn to the right, and in the south, they always turn to the left.
Toilets also.
That's a myth. Oh, really? Yeah. The scale is not big enough, but it's a really embedded myth.
Have a 100-mile wide toilet, it'll work.
I saw someone do a demonstration where they took a kiddie pool and let it sit over like 24 hours, and then you could see it.
You could see it,
right,
yeah.
right, yes.
I must admit, I did try when I went to the sauna, but it's not true. But, so what's being shown in that clip is the really extreme version of the Coriolis effect. And I believe, I looked it up, I believe he was supposed to be on Ceres at the time, which is this very large asteroid, but still very small compared to the Earth. And so you would get a much more extreme Coriolis effect.
So what is pulling the liquid in a different way?
It's trying to demonstrate that on the scale of that, the liquid, it's moving slightly faster when he pours it than when it hits the glass.
Wow.
So he must be pouring it kind of north or south relative to the equator of Ceres.
And that's why people were talking about it's an exaggeration because the scale is just not right, but it's super cool.
Yeah, it's super cool. And and I think so there was this thing about how, the rich people on the asteroid in Ceres live by the equator. They don't have to deal with this. But if you go kind of far away from the equator, you get a much more extreme version. And it's sort of supposed to be a hint that he's in the sort of economically depressed parts of the asteroid, which is kind of nice.
It's a fabulous detail.
Yeah.
That is, kudos to him. That's a fabulous, fabulous detail. In the 1990 version of Total Recall, in one of the top-rated villain deaths in cinema, Milos Kohagen gets sucked into the vacuum of space and his eyeballs explode out of its head. So it's a little shocking in The Expanse to see workmen occasionally open their visors while floating in space and their heads do not explode. So Charles was
My head explodes when I see that sort of thing. No, can we just diss Total Recall from 1990 for a few seconds? I got to tell you that movie had a remarkable impact on my life. We actually saw that movie in the theater with my then girlfriend, and this scene is like one of the climactic endings when the dome on Mars is destroyed and all this atmosphere is whatever, and this is transition between an instantaneous vacuum and an instantaneous terraforming of Mars, okay? So even that just originally set up is just crazy. But then I see Kohagen sitting there going, and his eyes bulge out, like, right? Meanwhile, Arnold Schwarzenegger is also sitting there, and, but his eyes don't bulge out because he gets saved just in time as the terraforming atmosphere comes in and then saves him. So he gets to stand up and go, oh, that was a close one. And I was just like, no. And there was still 3 or 4 minutes left in the movie, and I'm like, no, it's impossible. My girlfriend's like, come on. I'm like, no, you can't do that. And then I got up afterwards. I told her, this is terrible. That was just so horrible. It ruined the whole movie for me. And then a guy next to me, or a couple seats over, gets up and says the same thing. He's like, yeah, that was so unrealistic. This was horrible. It was a terrible ending. Like, oh. And the girlfriend's like, we're on a date, was really, it was a sad moment that's burned into my existence for the whole rest of my life.
Did Arnold Schwarzenegger ruin your love life?
Oh, no. Actually, I married her. We've been married for 30 years now, so started dating when I was 6. That total recall scene suggests that we have some sort of a perfect seal in our bodies that we can resist. There's pressure that's inside our bodies, adapted to atmospheric pressure here on Earth, about 14.7 pounds per square inch. So our blood pressure and our capillaries and all that sort of thing is designed to push outward at that pressure. And so when you get into vacuum, you just assume that like we're in a saran wrap or something like that, which will then bulge and bulge and bulge until such time as some part gives, and then poof, like a balloon, you pop out, right? But what actually happens is that we have plenty of other orifices and diffusive surfaces where liquid and gas will come flying out long before then. Our capillaries will pop, stuff will come out of our ears, mouth, etc., things like that. Our eyes will not bulge out like this and then bulge back in again, like a cartoon. That's not what happens. And so it's nuts. And we will actually suffer so much internal damage in the first few seconds that you wind up dying long before you can be restored back to health by some magical elastic recursion.
But you can,
Yeah, you can survive for like 30 seconds or more.
You can survive for 30
but
seconds.
You need like medical attention. Right afterwards.
Yeah, no, your eyes aren't. But
you're not going to go like this.
I mean, you're
right?
gonna be very cold.
Yeah.
And your blood vessels burst. I mean, I think honestly, I don't know that this has ever been tried. Right? We say you can survive for a few seconds.
That's a great point.
But has anyone actually tried?
Thank goodness there have not been controlled experiments about explosive decompression.
Ethical.
Yeah.
There have been people in like high altitude jets and people in like vacuum chambers and stuff like that.
Oh, really?
Yeah, they have like there's a thing called the Armstrong Limit, right? When you're in a high altitude jet, where the height at which you need to be so that like the pressure in your blood doesn't like rupture or something. But then also like NASA did a bunch of high altitude simulated tests on the ground with like how good their spacesuits worked. And so you'd have a test pilot in the space, and if the spacesuit wasn't up to snuff, then they would suffer decompression sickness and black out for a while, and then they would rush all the air back in and go rush them to the hospital, and they'd be fine eventually.
Oh, okay. So they got close, but not to the point
not to the hard
where eyeballs are
space.
blowing up.
Yeah.
All right, thank goodness.
In season 4 of The Expanse, humanity discovers a trove of habitable planets outside our own solar system via a ring created by a very powerful protomolecular plot devicey thingy. But in real life, how do we know from our vantage point on Earth that some distant planet is habitable?
Well, it is quite tricky, actually. I mean, one of the exciting things about the last 20 years or so of astronomy has been the explosion in knowledge of planets outside of the solar system. It's very, very hard to image a planet because they're very, very small compared to the stars they orbit. But we know now that several thousand of them exist, and current estimates are that 25% of stars may have Earth-like planets around them. Which
really?
is, yeah, right? That's like a really large fraction. They really just seem to be everywhere. And in terms of habitability, okay, so that's a little trickier, but there's this really neat concept called the Goldilocks Zone, where the planet is not too hot and not too cold. It's just the right temperature for life to exist. We can also do things like try to measure the light as it passes through the planet's atmosphere. So there's a method called transit method. It's this really cool thing where the planet passes in front of the star it orbits. And so we see a bit of the light from the star blocked out by the planet. And if you measure it really precisely, you can measure the light coming through the planet's atmosphere and get a sense of the composition of the atmosphere from that measurement.
Wow.
Yeah, it's cool, right?
Yeah. So a lot of geometry, a lot of math.
Yeah, I mean, and a lot of very high precision measurements made by some really, really nicely made instruments on telescopes. But yeah, I mean, so it's a really exciting area of astronomy, actually.
So the concept of a class M planet is a straight up Star Trek thing. Some Vulcan word. What do real astronomers call what the rest of us would refer to as a class M planet?
I think Earth-like has been maybe a little overused. So, you can use Earth-like for Earth mass, or do you mean that it has to also be at the right sort of distance from the star it orbits? Does it have to orbit a star that's like the sun? There's many ways planets can be Earth-like, but you will you can read a lot about Earth-like planets being discovered. So
Do you think are we moving? Should I pack?
they're a very long way away. So unless we find the ring or the warp drive, it's not going to be a trip that we're going to make.
At the fastest speeds we've ever sent spacecraft, the nearest star with a terrestrial type planet will be about 80,000 years away.
Oh, wow.
Space is big.
Space is big.
Yeah. This is so, we should take care of our house.
Yes.
Yeah.
Because it's the only one we
It's
have.
a lot easier than the alternative.
Yeah, definitely. They never say in the show what year all of this takes place in, but I would like to get your sense of how close we are to that kind of world.
It's got to be hundreds of years.
Yeah, there are different things in the universe there that are different sort of levels of advancement, I feel like. Like some of the spaceship technology may be like 100 or 150 years away, but some of the things like having a really populated Mars might be 300-400 years away.
The energy.
Yeah, the joke is that fusion energy is always 40 years away. So not only do they have to have finished getting perpetually 40 years away, but also miniaturizing it and making it so efficient that you can power a spaceship for that long. That it's really, it's going to be an effort to get there.
You kind of get a sense from the story as well that this has been a world that's been like that for a while, right? They've sort of developed these cultural differences from the Belters to the even Mars and Earth are very different. So you really get the sense that they've been doing this kind of space travel for many generations at the point the story is happening. And we are probably several generations away from being able to do that kind of space travel. So
The more I think about it, the more I think that the Expanse is literally a millennium away.
Really?
The technology, of course, we cannot imagine how much technology will advance in 1,000 years. But the human aspects of what we know, if they're using this kind of technology to travel around the solar system or from asteroid to asteroid or whatever, then by the same token, how did they get 1 billion people to Mars? Or how did they even get 1,000 people out to the moons of Jupiter and actually have labs, space, real cities, with red light districts, that kind of thing. That's a long, long time.
I think a millennium's too long.
You think so?
I think that because there's so many more people to do discoveries and so much more technology that we have that enables more technology, that I think that the next 500 years are going to be more technological advancement than the past 3,000 years.
Oh. Well, okay. In that
right.
case,
That's
I would be an overestimate, yeah.
But even if you think 200 years ago, what the kind of technology was that was standard, things are very different now, right?
Yeah. And it's,
Very different.
Yeah.
So,
Well, have we reached any limits is an interesting
That's another question.
Right, we've hit a quantum barrier. We understand there's a speed of light barrier now. The rocket equation is a tyrannical piece of mathematics. So maybe we just happen to be in a nice location in the past 200 years of technological development where we could burn a lot of fossil fuel and get a whole bunch of electrical benefit from the electromagnetic force that we did not have until about 1800 or so.
Niron Shankar, the amazing showrunner of The Expanse, has a bit of a crazy quilt education, starting in liberal arts at Cornell, wandering through medieval studies and French literature before transferring to the College of Engineering, where he stayed until he got his engineering doctorate, and then went to LA to write for TV, and they don't say it on the wiki, but that whole thing drove his mother crazy. But the real question is, does art need science, and does science need art?
yeah, I mean, I'm a firm believer of the two kind of being intertwined and helping each other. They're just both ways for humanity to express its creativity, and I think that we need both.
Yeah.
Albert Einstein once said that the true origin of all art and science was rooted in the same sense of being awed by the mystery of the cosmos. And so all great art and science, even all ordinary art and science, are intertwined because they are coming from the same origin. Mm. You could trace back, at least in European history, to about the 1600s, when Galileo Galilei was first explaining, look, empirical science is different from the natural philosophy of the beauty of a tree or something like that. And he got pushback from the philosophers of the time, and he just said, look, I'm going to tell you all, from now on, when I talk about the natural world, I'm going to use numbers, I'm going to use measurements, empirical data to measure that. And thus sort of began a schism between art and science. That's not necessary. It's practical because both areas are such big enterprises that it's hard to be an expert in both. But if we ignore one at the expense of the other, I think the results of both drop in quality and in quantity and in value.
You want a piece of that?
Yeah, sure. I mean, that's a really great way of putting it. And I think that's why ideas of like things like science fiction are really intriguing, because it lets you use the science to explore the world in ways that you couldn't otherwise, in ways that let you think about humanity in these new and interesting ways to see, are we still the same people if we're spread out across the solar system and beyond?
Sure, that piece of art started us talking about what our where humanity is going.
Yeah.
Yeah. Unfortunately, tragically, we are out of time. We're always out of time. I hope that you will come back again and we'll talk about more things. Thank you for joining us.
Thank you
Thank
so
you.
much for having us. It's such a pleasure. Thank you.